Started, right?
Yeah,
All right, perfect. I'm Lucas,
and my name is Diwas.
and for our final project, we chose to look at modeling epidemic dynamics using compartmental models and networks. Um, our primary objectives consisted of using compartmental models like the SIR and SEIR models and network theory to simulate the spread of an epidemic in a population. Our model approach was to create a continuous time deterministic model where we use differential equations to model the outbreak of disease spread. We incorporated network-based transmission dynamics where individuals are nodes and edges represented by a contact relationship. Then we used network analysis to evaluate the effect of different topologies like small world, random, or scale-free networks to look at the spread of disease. We validated our model using real-world COVID-19 data, specifically from the United States and Canada. Finally, we submitted and analyzed how the underlying network structure affected the epidemic spread. Before we designed our model, we looked at some relevant projects to help us through the thought process and design of our model. First, we looked at the project of epidemic processes in complex network. Pastor, Sartors, and others designed a SIR network model that analyzed disease spread in urban areas by representing networks as interconnected nodes and accounting for daily population movement between them. Using data from the 2008 Rio de Janeiro dengue outbreak, the study found that incorporating dynamic infection rates significantly improved the model's ability to capture the epidemic progression. Another related work that we studied was the project robustness and fragility of the susceptible infected susceptible epidemic models on complex networks. Wesley Coda and researchers used a stochastic SIR model on dynamic networks to model the pre-vaccine epidemic state of whooping cough. Their main findings were that network properties influenced infection dynamics, with distributions of infected individuals showing gamma and Q exponential patterns. Their results linked disease transmission rates to correlations between susceptible and infected neighbors, which highlighted the limitations of traditional homogeneous SIR models. Both of these research projects do work using networks with homogeneous SIR models like we wanted to do in ours. However, our goal was to research and understand the different network effects. We started our project out by gathering data, which was generated by creating a network of interconnected nodes using one of the three possible random network models. We started off with these small world model, a random model, or a scale-free model, as you can see over here in the code. This is how we did that. For the random networks we generated, we used the Erotos-Rini model, where each pair of nodes has a fixed probability of being connected. You can see this in the code. The small world network we used was created by the Watts-Strigatz model, which combined a regular lattice with random rewiring of edges. And finally, our scale-free network is created using the Barbasi-Albert model. This model generated nodes that preferentially attach to existing nodes with high degrees. This creates a power law distribution, and once the network is generated, the codes run the SIR and SEIR disease spread simulations on this network. So we pretty much replicated these three different network models and then ran the SIR and SEIR disease models on them. And you have, Dewis, you're showing like this is the part of the code, right?
Mm-hmm.
Okay, perfect. Then for each step in the simulation, our models computed the proportions of susceptible, infected, and recovered for the SIR model, or susceptible, exposed, infected, and recovered for the SEIR model. For our network, we considered the transmission rate beta, recovery rate gamma, and incubation rate sigma. To prove whether generated data would be a good predictor, we also used a data set from our world we used the data set from the real world, a COVID-19 data set that had infectious statistics. Specifically, we focused on the data from Canada and the US, like I said before, but we highlighted the period from March 2020 to October 2024. And now I want to pass it back to Dewis, who's going to talk about the results of our experiment.
Mhm. To reiterate our hypothesis, we wanted to look at how underlying network structure influenced the epidemiology outcomes of a disease spread. We modify our initial SRI, this was our initial SRI models and SEIR models, and with a time step of 300. And then we did try to initially start with, I think, yeah. So for our example, with the basic SRI model, we had 1,000 nodes, and so our graph pretty much sees this is just the basic implementation without any network, so it looks like the basic model. But then for this one with the network structure, where did the graph go? So when we actually ran the different models, here's what our graph looked like. And this was for initially, we did it with 100 nodes with T step of 365. That was to represent the number of days in a year. And as you can see with the small world, both SRI and SER models, and this was for 100, this was for 1,000, and this was for 10,000. Going any further would just kill my kernel. I wasn't able to run anything above 10,000. And as shown in the small world figure, small world networks, both SIR and SER models, exhibit a fast disease spread due to the network combination of local clustering and short average path between nodes. The high clustering allowed rapid spread within local communities, while the small length ensured the disease can easily reach a distant node. This reduced the threshold for epidemic outbreaks. In the SRI model, the infectious peaks more quickly as infected individuals spread the disease immediately. And in the SER model, there is a slight delay in the spread due to the exposed stage. But once the individuals become infectious, the disease spreads pretty quickly. As you can see right here, the recovery rate like shots up through to the roof, and same with the susceptible, just dropping it into almost an L-shaped line. And with the scale-free network, right here, the scale-free network displays the dynamic of model 2. And in the SRI graph, the susceptible population declines rapidly. Now, this is almost like the grid itself. It's just sharply dropping it, followed by a steady increase in recoveries and a epidemic resolve. And so in contrast, the SIER graph incorporates an exposed stage, introducing a delay before an individual become infectious. The result is more gradually declining in the susceptible population. The exposed population peaks before infection rises, while the recovery curve stabilizes later compared to the SRI model, indicating a lengthy endemic dynamics. The result highlights the role of hubs in driving a rapid outbreak and suggests that the targeted interventions such as vaccination or isolated, highly connected nodes could mitigate the spread, which we weren't able to model vaccinations simply due to not having enough time. And then going back to the middle network, for the random network, we reduced the initial size. I think, yeah, before we ran this, we were trying to run big numbers. We couldn't do it. So again, running to 10,000 nodes. So in the network model with SRI, there's a sharp increase in the infection rate during the early time steps around here. Again, this is pretty similar to the SRI model for a scale-free network, leading to a steep decline in susceptible population, while the recovery rate follows a similar pattern. And in SRI model, the exposed compartmental shows slower infection spread, but it still follows the general SRI trend with the noticeable spike during the initial timestamp. Again, right here, it's pretty peaked up, but like with the exposed, and then the infectious is slowly like following that normal curve. This suggests that the modeling exposed, but it still follows the general trend with the noticeable spike. This suggests that the model disease spreads in random network is most effective when the disease is highly infectious. Also, random network don't necessarily represent all real world accurately, so and then we did try to do a curve fitting with, and for the last part, we did try to do a curve fitting with the first 3 months of the pandemic. Going any further, like we could graph this going up to like 6 months, but like when we actually tried using the network model to connect it, it was just taking too long for it to like actually generate anything. And then also, we had to use homogeneous edge connection between nodes for different networks. When we tried checking infection probability based on neighboring nodes and applied that to a curve fitting, it took too long to run. Again, just the computational power our laptops doesn't have. And as you can see, we did the simple model. The network is actually not being used here, so we're just assuming that every node is connected. And one thing we noticed was we also calculated the RSME and then the coefficient. It just shows that 24% of the variability here is explained. And then this was for the thing we used network. Where did it go? No, I'm pretty sure this was small world. Nope. So this was random. No, I think this was the scale free. Yeah, we used scale free model for this one. And then we just repeated that same process, but with different SIR and SIER models. And as you can see, we had a pretty shitty comparison of the whole model. But then when we included the exposed with SEIR model, we got a higher R squared coefficient, suggesting that if we change from a simple SRI model to a little complex with exposed, it gets better. And then just for sake of it, we also try to do this is for SEIR. Yeah, no, this is for SEIRS, which was, yeah, SEIRS. So it's like infected, exposed, susceptible, and we had a better R square coefficient, suggesting that with different models, different compartmental models, and different networks, we can actually stimulate how a pandemic would occur in our real life. Specifically, seeing this 87% coefficient with the SRI model or SEIRS models.
Oh, the future work now?
Yeah.
Yeah, so for our project, it was like figuring all this out and doing all the calculations for the different types of models and then interpreting the results. We realized that our project was quite ambitious, but in the end, we didn't really have enough time to try everything that we originally thought out that we would, such as the vaccination rates, as Dewis mentioned, or the idea of lockdowns. And then going back to what Dewis said about the computational power that we had, that we needed to simulate the different network models, simply just wasn't enough. And it just like didn't really work as well on our computers. Pretty much the sheer size of the data exceeded our computer's capacity, which then prompted us to scale down the network and run the simulations effectively. To extend this project in the future, we could simulate how variations in social distancing measures or changes in contact behavior influence the spread of an epidemic, or we could actually incorporate the vaccination and lockdown effects that we originally set out to do. One way that we thought about going about this was by introducing a time varying transmission rate beta. This would reflect the effects of intervals or interventions or lockdowns over time. This would allow us to model more realistic epidemic dynamics and evaluate the impact of different public health strategies. And this time, spend longer time researching a different hypothesis for or SIR models.
That's it.
Yeah, that's our prod. Do you have anything else to add to us?
No, that was it.
All right, perfect. Thank you.
Thank you.